Welcome back. Let's go ahead and hit up another important point about these critical numbers and local mins and maxes, and then we're going to talk about global maxes and mins and how to find them if they exist at all. So, small detail we should definitely talk about before moving on. Let's find all the critical numbers of f of x equals x cubed. And there's a couple of ways that we could think about this. The first you should do, boy, is life easier if you know roughly what a bunch of simple functions look like. F cubed looks a little bit like this. Okay, and if I wanted to, I could go ahead and find f prime of x and say this is 3x squared. And I could set that equal to 0. And what you see is that I have one solution to this, which is just 0 equals x. And if you count your multiplicities, it actually is a multiplicity of 2, which is telling you something interesting as well. So we have a critical number of 0. By the way, that derivative is defined everywhere, so I don't need to worry about where it's not defined also being a critical number. But this is my only critical number. Now, is it a local max or a local min? If I was going to play the same first derivative test chart game, then what you'd see is that, well, it's a 0 at 0, but that derivative is positive for positive numbers and positive for negative numbers. And we see that here, right? It's going up, it flattens out, and it's going up. If I did this perfectly, it would almost look, it would look like it flattened out just for like an instant. It instantaneously flattened out and then kept on going up. So it should have a horizontal tangent line right there at 0 if I drew it right. Notice this is not a local max or a local min. This doesn't have any local maxes or mins. This doesn't have any global maxes or mins either. Okay. The other test, just to try to make this as connecting to other sections as possible, is our second derivative test. And just to kind of verify this again for a third way, if I looked at f double prime of x and we said this is 6x, well, we could see that at 0, that's also 0. And this has this oddly inconclusive feel to it. It's neither positive nor negative. So just to show that like math isn't leading you astray, it tends to point out when its own rules break down to you. Okay, so you can have a critical number that is not a local max or a local min, and any way you want to look at it, whether like pictures or first derivatives or second derivatives, will just reinforce that. All right, so what about global extremes or extrema? We have a nice theorem that lets us know when they exist, or rather a nice case where you know they have to exist. So it's called the extreme value theorem. If a theorem has a name, it is probably important. If it's not just theorem 1 or 7, if it's got a name, it's probably important. So the extreme value theorem, sometimes called EVT, says if f is continuous on a closed interval AB, notice it's closed, so it includes those endpoints, very important, then f attains an absolute max and an absolute min on AB, on that closed interval. So this works basically when you know you're continuous. Here's that word again, another reason why continuity is so important, and when you're closed. So let's just take a look at some quick pictures of when this works and when it doesn't. In this first case right here, notice it's just a nice closed interval. It looks like a line. Here's my local max. Here's my global max. And here's my global min. Okay. This next one is also a fits. It's continuous. It's closed, and it has a global max at that local max, and it has a global min at that local min. So in this next case, you can see that we have a local maximum that is our global maximum and a local minimum that is our global minimum. Both of these satisfy the conditions. They are continuous and they are on a closed interval. However, this next example, you'll notice, does not satisfy either condition. Right? So right here, that's a discontinuity, and that's causing some trouble. Plus, you'll notice it is on an open interval. This one has no global max or global min. If it did, you should be able to point to it. And while I kind of want to point right here, that point isn't there. It's not in the domain. And I kind of want to point at the other one, and that's not there either. So you see how having a discontinuity can help you kind of break the results of the extreme value theorem, and also how having an open endpoint can do that too. Similarly, yes, open endpoints, but also asymptotes. The vertical asymptotes are always going to be discontinuities. And in this case, we don't get a global maximum either. There is no maximum. It gets as big as you want. Even if I continue this function with a closed circle here, right, there still would be no global maximum because it grows as high as you want, and that happens with the discontinuity. So something I often encourage people to do is see if you can break it. This is a good way of convincing yourself that the extreme value theorem works. So if it's on a closed interval, it should start at some closed circle and end at some closed circle. And if it's continuous, I should be able to draw a function from left to right that connects these two without lifting my pen. And see if you can do that in a way that wouldn't give you a maximum or a minimum. So I could try to go really high, but then I got to come back down. And the second I come back down, I've given myself a maximum. Well, if I wanted to undo that, I'd have to kind of try to go higher, but I still have to come back down to reach this thing. So no matter what I do, I'm sort of stuck from getting from one to the other in creating maximums or minimums. Even if it's something really silly, like a horizontal line, it still has a global maximum and a global minimum. It just so happens that the max value and the min value is the same thing. Okay, so it's kind of worth just taking the 10 seconds and seeing, could I make something that breaks this extreme value theorem? And it's a nice way of convincing yourself how and why it works. Okay, so from the extreme value theorem comes a method for finding global maximums. And it only works, or it's only guaranteed to work, if I'm continuous and I'm on this closed interval. So here's how it goes. We say we know how to find all local maximum and minima, and that's by looking for critical numbers. So step one is that I find all the critical numbers on the open interval. Step two is and by the way, I find their values. I say, how big is their function value? How big is the y value? There should be finitely many, and usually for examples there's just a couple. I know how to do that thanks to Fermat. Then I find the values at the endpoints, because those are the only other possibilities that wouldn't be covered by Fermat's theorem. And then finally, once I have this list of possibilities of endpoints or local max or mins, I just compare them. I just plug in and say, what's the biggest or the smallest? It's a really nice finite check to do. It's an elegant solution that works quite well. So let's go ahead and do this with our old friend. We already used this as an example once, so I'm going to go a little faster through this derivative here. Let's go ahead and find y prime. It's the exact same function as before. We get 12x cubed minus 48x squared plus 36x. I check to find the critical numbers, so I say, does this not exist anywhere? It exists everywhere. That's really nice. Next, I say, where is this 0? And to do that, I'm going to factor it out. And I believe what I did is I factored out a 12x, and I got an x minus 3 and an x minus 1. Okay, so I did that pretty fast because we've already done it once. And so I get x equals 0, 1, or 3. And let's go ahead and actually turn this sideways and say, at x equals 0, 1, or 3, what are my function values? F of x would be, and I just plug in. So if I plug in a 0, I get out a 0. If I plug in a 1, can you do that? If I plug in a 1, I get 3 minus 16 plus 18. So that should be 5. Whereas if I plug in a 3, if I plug in a 3, I got to actually do this. 3 times 3 to the 4th minus 16 times 3 to the 3 plus 18 times 3 squared is negative 27. Okay, so those are our possible candidates so far. We should still go back and say, what about my endpoints? So my endpoints are, oh no, I didn't give you any endpoints. Shoot. So my endpoints are, let's go ahead and just add those in now. Sorry, team. I had them up above. So we're going to go -1 to 4. Okay, -1 to 4, nice closed interval. So I should check those endpoints as well and say, okay, well, what happens if I get a -1? And what happens if I get a 4? So if I plug in a -1, I get 3 plus 16 plus 18. Can you do that math? That's going to be a 37. Okay. And if I do a 4, then I'm going to get, well, I can't do this one in my head, so I'm going to put it in my calculator real quick. 3 times 10 to the 4th, sorry, 3 times 4 to the 4th minus 16 times 4 to the 3rd plus 18 times 4 squared. Oops, let me try that one more time. 3 times 4 to the 4th minus 16 times 4 to the 3rd plus 18 times 4 squared is going to be 32. Okay, so people often get confused here. Remember that you are plugging it back into your original function. I want to know how high or low they are. I'm not plugging it back in to my y prime. Okay, so from here, all I got to do is find the biggest and the smallest. So it looks like, hey, here's my biggest, and my smallest is going to be right here. Okay, so in other words, we have a absolute max of 37 at -1, and we have an absolute min of -1, sorry, of -27 at 3. Ta-da! That simple. So for most of the cases, this is going to work out pretty darn well. If it's continuous, then usually we'll have a derivative everywhere. I should note that, hey, if I thought about absolute value of x, this has a critical number at 0, okay, or of 0, because the derivative doesn't exist at 0. So these last two examples, the derivative always existed, but we should also check here. In fact, the global minimum on any domain, including 0 here, is going to be at 0 for absolute value of x. So we do need to check where the derivative doesn't exist. Okay, let's do one more, and then maybe two more. Let's find the global max. Let's find the global max of this function on -1/2 to 4. Give it a second, try it on your own, and then I'll follow behind you, which means pause the video. Okay, here I go. Y prime is equal to 6x squared minus 12x plus 0. I want to find where is that 0 to find my critical numbers, because it is defined everywhere. So I'm going to factor this out. Looks like I would get 6x times x minus 2. If I factored that out right, I think I did. So in other words, x is equal to 0 or 2. Nice and easy. All right, let's go ahead and check. You don't have to make a table, but tables present your work nice. I got to worry about an x of 0. I got to worry about an x of 2. I have to worry about an x of -1/2. That's my endpoint. And I need to worry about an x of 4. So I'm going to plug each of these in. At 0, I get a 5. Take a second. Play on along with me with a calculator. See what you get when you plug these into your original function. So if I get 2 times 3 cubed minus 6 times 3, oops, I don't know why I'm doing 3's, 2 times 2 cubed minus 6 times 2 squared plus 5 is going to be a negative 3, whereas 2 times 0.5 cubed minus 6 times 0.5 squared plus 5 is equal to 3.75, whereas finally 2 times 4 cubed minus 6 times 4 squared plus 5 is equal to our old friend 37. Okay, now it's just a matter of comparing. Looks like our biggest one is 37, and our smallest one is negative 3. Okay, so sometimes people will just give points on these. So we'll say our absolute max is 2 comma, sorry, that's my min, is 4 comma 37, and my absolute min is 2 comma negative 3. Great. All right, that's basically the game. You do a couple of them and they start to make sense, but make sure the picture in your head makes sense as well. I would be remiss if I didn't remind you, hey, why do we care? Why do we care? And it turns out we care because finding the best and worst of things is what a lot of math is used for out in the world. Finding the cheapest way, the fastest way, the strongest way, the most potent way, the end result of the lowest energy result of a reaction, the most profit, all those things. So one quick kind of leading example to wrap this up. Let's come up with a silly way of thinking about an optimization problem. And optimization is definitely in your future. So theoretically, one last problem. Your happiness after t hours of math is modeled by 10 e to the negative t minus 7 squared units of happiness, where t has got to be between 0 and 24. That's the number of hours in a day. What is the optimal amount of math to make you the happiest? I think about this a lot. I often wonder what's the best amount of math to do. So I'm going to give this a try. I wanted to do one that wasn't a polynomial as well. We're really just finding a maximum with a t. So I'm going to say that my y prime, or my f prime, is equal to the derivative. Well, that 10's going to hang out. Oh, got to do a little product rule here. E to the stuff times, all right, the derivative of that stuff is going to be negative 2 t minus 7. And then if you wanted to do another product rule, quotient, chain rule. If you want to do another chain rule here, you could. The derivative of t minus 7 is just 1. Sorry, chain rule is the whole way through. Great. Looks kind of long. Let's see where that is 0. So if I said 0 is equal to, I'm going to bring this negative 2 and 10 out front, so negative 20. And let's take this t minus 7 out front as well. E to the negative t minus 7 squared. Great. One thing I can do if I'm trying to solve for this, first off, I should point out, by the way, this exists everywhere. So I don't need to worry about where the derivative doesn't exist. I could divide both sides by negative 20. That is perfectly okay. And if I do that, this goes away, because 0 over negative 20 is 0. What you might not realize is that I can divide by the e to the stuff. But another way of thinking about this is I'm going to solve this for each of my factors independently. And I'm going to say when is 0 equal to t minus 7. That's why we factor, is so that we can deal with them separately. I'm going to say when is 0 equal to e to the negative t minus 7 squared. Okay, so the one on the left is pretty fast. This is when 7 equals t. The one on the right, do you know it? Okay, this never happens. E to the stuff is always positive. You never get a 0 out. So there's no extra solutions given to you by this, which is why you're always allowed to divide both sides by e to the stuff, is because you'd never be dividing by 0. Great. So we really only have one point to look at. And you should ask yourself, is it a positive, or is it a maximum or a minimum? But actually to do that, we can just do our extreme value test in this case. So let's go ahead and do that over here. X could be, it could be a 0, it could be a 7, or it could be a 24. Okay. If I plug in a 0 into my original function, what do I get? If I plug in a 7 into my original function, what do I get? If I plug in a 24 into my original function, what do I get? Take a second, give those a shot. I'm going to justify this to you right now and say if you graph this thing, you kind of have a nice bell curve shape. And so you should expect that what you're going to get out is a maximum, is that local maximum is also your global max. So sometimes it is enough just to know the shapes of these curves or to graph them to realize this value right here, your global max, is at 7. So go ahead and plug in those numbers and make sure you get it, that it agrees that this is the biggest number. But also just plotting it, you can see that our global max should be at 7 hours of math a day is the optimal amount of math to make sure that you've optimized your happiness units for your life. Okay, that's it for now. Hopefully it's a little interesting. We will use this stuff a lot in our optimization section.